So in an earlier lecture we spoke about reverse completely inelastic collisions, and I gave two examples of such collisions. First being explosions, which we spoke about earlier, and the second one being radioactive decay. Now in this lecture we're going to focus primarily on radioactive decay. Now most atoms found on the periodic table undergo the spontaneous process of radioactive decay, in which a section of the nucleus of the atom breaks away from that atom. So what determines the rate at which the nucleus breaks apart? Well, it turns out that the more unstable an atom is, the more unstable the nucleus of the atom is, the more likely that atom will undergo radioactive decay. So, the larger the number of protons found in the nucleus of an atom, the more unstable that atom. And that means if that atom is more unstable, it will have a higher rate of radioactive decay. In fact, all atoms with 83 protons or more will be unstable, and that means they will have a relatively high rate of radioactive decay. Now for smaller atoms, the ratio of proton to neutron determines how unstable that atom is. So for example, if an atom has 8 protons and 8 neutrons, because the ratio is 1:1, it will be considered stable, and that means it will have a relatively low rate of radioactive decay. In other words, for smaller atoms, if they have a ratio of protons to neutrons of 1:1, they will have a low rate of radioactive decay because they will be considered relatively stable. So it turns out that 3 things determine our stability of atoms. 1 being the number of protons found in the nucleus, 2 being the number of neutrons found in the nucleus, and 3, for smaller atoms, the ratio of protons to neutrons should be 1:1. So, there's also something called a half-life of an atom or element. Now the half-life is simply the time required for a certain amount of pure substance to fall to half its original amount. So let's look at the following example to gain more intuition about what a half-life is. So the half-life of a carbon-11 atom is 20 minutes. If we begin with 100 grams of carbon-11, how much do we have left over after 60 minutes? So we are given that the half-life of a carbon-11 atom is 20 minutes. That means after 20 minutes, we're going to have exactly half of our original amount in grams left over. So if we begin with 100 grams, that means after one half-life, after 20 minutes, we're going to have 50 grams of carbon-11 left over. Why? Well, because it took 20 minutes for our relatively unstable molecule, the carbon-11 atom, to break away. In other words, exactly 50 grams of its nucleus broke away from its original atom. And we have now 50 grams of carbon-11 left over. Now after one more half-life, after 2 half-lives, or after 40 minutes, we have 25 grams left over. Because after 20 minutes, exactly 25 grams of this, or half of this amount, was decayed or decayed. Now, what happens after one more half-life occurs? What happens after 60 minutes? Well, half of this decays, and so we are left over with 12.5 grams of our original carbon-11. So after 60 minutes or 3 half-lives, we have 12.5 grams left over. So now let's look at the different types of radioactive decay that exist. So now let's look at the 5 different types of radioactive decay. Let's begin with alpha decay. Alpha is simply the Greek letter alpha represented by this symbol, so that's why we have alpha decay. And an alpha particle is simply a particle that has 2 protons and 2 neutrons. And because a helium atom also have 2 protons and 2 neutrons, that means an alpha particle is simply a helium particle. So what happens is our atom undergoes alpha decay and loses an alpha particle. So it loses an alpha particle and forms a different atom with a different number of protons and a different number of neutrons. So let's look at the following example. So, suppose we have the atom given by the symbol U that has 92 protons and 240 nucleons. So that means it has 240 minus 92, which is 148 number of neutrons. So if this atom undergoes alpha decay, it forms the following alpha particle, a single alpha particle, and a new element. Now this alpha particle has 2 protons and 4 nucleons. So 4 minus 2, it has 2 neutrons. And it also forms a new atom that has 2 less protons than before and 4 less nucleons than before. So 92 minus 2 gives us 90 protons. So the atom is represented by this symbol TH, and it has 240 minus 4, so 236 nucleons. That means this atom has 236 minus 90, so it has 146 neutrons left. And this is known as alpha decay. So, what types of atoms undergo alpha decay? Well, atoms that have a very large number of protons found in the nucleus are relatively unstable. And that means if the number of protons in the nucleus is large, that atom will undergo radioactive decay in the form of alpha decay. So it turns out that atoms that have 83 protons or above will undergo alpha decay. So let's look at decay number 2, called beta decay. Now beta decay is represented by the symbol beta, so beta decay. And beta decay involves the loss of an electron, which is called a beta particle, from the electron cloud of the atom. So let's look at the following example. Suppose we take this product of this reaction and let's make it the reactant. So now this is our atom that is undergoing beta decay. So it has 90 protons and 236 nucleons, so 146 number of neutrons. So let's suppose it undergoes a beta decay and it releases an electron atom, so a beta particle given by this symbol, where E simply means electron and -1 simply means it has a charge of -1. Now the 0 simply means it has no neutrons. So what happens? Well, note the following happens. We go from 90 protons to 91 protons. So a new atom is formed. Why? Because the charge of this guy and this guy must be neutralized. Before we had a neutral charge, and now we also must have a neutral charge. So we have -1 and +1 proton. So that means that whenever beta decay occurs, there's a proton that's created along with our electron. So what actually happens is there's a creation of a proton and electron from a neutron. So a neutron is destroyed. In other words, look, before we had 236 minus 90, so 146 number of neutrons. And now we have 236 minus 91, so only 145 neutrons. We have 1 less neutron. What types of atoms undergo beta decay? Well, those atoms that have very high number of neutrons found in our nucleus undergo beta decay. Now, let's look at a third type of radioactive decay known as neutron emission. Now, a proton decays and creates a neutron. So let's look at the following example. Suppose we have a carbon-11 atom that has 6 protons and 5 neutrons. And suppose it undergoes positron decay. So that means 1 proton will decay, will be released from the nucleus, forming this positron, which has the same charge as an electron, except now it's positive. So that's why the 1 is here and the 0 is on top, because it has 0 number of neutrons. So that means this atom will have 1 less proton. It will have 5 protons, but now it will have 6 neutrons, whereas before it only had 5 neutrons. So a positron decay actually creates a neutron and releases a proton from the nucleus. So let's look at the fourth type of radioactive decay, known as electron capture. Now, in an electron capture, an atom takes in an electron and combines it with one of the protons found in the nucleus to form a neutron. So an electron and a proton are destroyed, but a neutron is created. So let's look at the following example. Suppose we have a potassium atom represented by the letter K that has 19 protons and 40 nucleons. So it has 21 neutrons because 40 minus 19 is 21. So what will happen in an electron capture is this atom will take in an electron, combine it with a proton, destroy that proton and electron, and instead form a neutron. So we will form another atom that has one less proton but one more neutron. So we will form an argon atom that has 18 protons and 22 neutrons, whereas here we have 21 neutrons because 40 minus 18 is in fact 22. Now, what else is released in electron capture is electromagnetic radiation known as gamma radiation, symbolized by this Greek letters gamma that has a 0 charge and a 0 mass. So it's simply electromagnetic radiation. Now let's look at the final type of radioactive decay known as gamma decay. Now in certain instances, mass is destroyed, releasing energy in the form of radiation, according to the formula E equals mc squared. And I'm going to talk about this formula, which is known as mass defect, in another lecture. So let's look at the following example. So let's see what happens when the proton combines with an electron. So when a proton combines with an electron, it releases electromagnetic radiation in the form of gamma rays. So it releases two gamma rays that both have a mass of 0 and have a charge of 0. So mass becomes electromagnetic radiation or energy. That's exactly what we saw in this case when this gamma ray was released.